Hello, my name is Daniel Grimmer. I'm a DPhil student at the University of Oxford studying philosophy of physics. In particular, I've been working in the metaphysics of space and time recently, and I've got a view I'm putting forward in a paper about deflating spacetime. So it's a dynamics first view of the spacetime manifold. I'll explain what that means throughout the talk. So first, though, as a primer, I should review the metaphysics of laws debate. There's a class of views here which I'll call dynamics first views, and these are along the lines of Hume and Lewis, that the laws of nature are merely codifications of certain patterns in the dynamical behavior of matter. After this, I'll briefly review the dynamical versus geometrical spacetime debate, and similarly here there's a class of views which I'll call dynamics first views of geometry. These are along the lines of Harvey Brown and Nick Huggett. They say that the world's geometric structure, for instance in special relativity, this would be the Lorentzian metric and the connection, are merely codifications of certain patterns in the dynamical behavior of matter. So once I've reviewed these two debates, I'll sort of unite them in a larger scoping debate, which is dynamics first versus dynamics second debates. Then, once I've united these, I'll make room for a third new debate to be launched, which is about space-time and the space-time manifold. So whereas the first two debates were about laws and geometry, this third debate will be about the world's topological structure and about the space-time manifold. The analogous claim, which I'm going to put forward there, is that the world's topological structure, so the space-time manifold itself, is merely a codification of patterns in the dynamical behavior of matter. So that's the view. And then I will demonstrate this with a few example applications. So let's just jump into it. We have the metaphysics of laws debate. A question at the center of this debate is, can the laws of nature help us explain the dynamical behavior of matter? Questions arise such as, why did this apple fall? Why do these like charges repel? And why do my two light clocks tick at different rates when I put them into relative motion? And if we're allowed to appeal to laws, we have some stock answers to these questions. Apples fall because of the laws of gravity. Similarly, charges and light clocks are governed by the laws of electromagnetism. In general, things happen as they do ultimately because the laws of nature govern them to that effect. These are some answers you might give. Do we like this laws to dynamics explanatory strategy? We can stop and ask. What sort of metaphysical backstory is needed in order to support this strategy? So the question, again, is why did this specific dynamical phenomena happen? And the answer is because the relevant laws of nature govern the world to that effect. And I should note here that the arrow of explanation points from laws to dynamics. So dynamics are being explained in terms of laws. And in my nomenclature, this makes them dynamics second views of laws. So the nomenclature comes from the direction of the arrow of explanation, and then you look at where dynamics is in this, so dynamics second views of laws. So if you take these sorts of explanations seriously, though, or taken literally, I mean, then this view seems to suggest that the laws of nature are some metaphysically substantial things in the world which reach out somehow and cause the particles to move as they do. But all sorts of metaphysical questions arise if you try and give that sort of explanation. What sort of a thing is a law? Where do they get their sort of gnomic voltage from? How do they push things around? How do they push the matter around? Why can't the particles and fields push back on the laws? Some, including myself, find this sort of explanation pretty suspect. Fortunately, though, there are also metaphysically deflationary accounts of laws which we can fall back on. So let's consider one of these deflationary accounts of laws in the style of Hume, David Hume or David Lewis, although I'll distance myself from them in a bit. But let's go along with them for now. So they might say the laws of nature are merely codifications of certain patterns in the dynamical behavior of matter. So this is a very metaphysically deflationary view of laws. And in particular, according to Lewis, the laws of nature are those which best balance simplicity and strength in terms of their deductive consequences. So the arrow of explanation here is reversed. It points from dynamics to the laws. So we'll call these dynamics first views of laws. The primary benefit of such a view is its metaphysical sparsity. All we have is the sort of Humean supervenience basis, the substrate which we will codify into laws. So whatever is involved in the dynamical behavior of matter. The primary cost of these views, however, is that we lose access to law-based, metaphysically supported explanations of dynamics. And I say metaphysically supported here because there is a sense in which laws are explanatory by unifying things. So you get a unified explanation of why apples fall and why the moon is moving as it is, and you sort of unify quite a variety of phenomena under the law. But if there's nothing metaphysically substantial to the law, we can't really have a metaphysically supported explanation of why these things are happening the way they are. So, and maybe you want that from a law and maybe you don't. Right? But those are the sorts of explanations we lose out when we don't treat laws like metaphysically substantial things. So some imagery which is associated with these dynamics first views of sort of Lewis and Hume is the Humean mosaic. And I'm here dealing with a generalized Humean mosaic, and I'll say why it's generalized in a moment. But in general, you sort of see the world as a grand painting of many properties. Right? So there's properties and they're spread out in space and time, painted onto a wall in some way. And confronted with such a view, a dynamics first view, two sorts of questions will arise. Laws codify which patterns? So how am I supposed to look at this mosaic and read off what the laws are? Lewis has his best systems analysis, although there are others. Right? The second question, though, is what is the paint? So the paint is supposed to represent the dynamical behavior of matter, whatever sort of metaphysics goes into that, maybe their properties, categorical things, dispositions, and this is where we start to go away from Hume and Lewis. Right? And this painting, by the way, is the Great Wave off Kinagawa by the Japanese painter Hakusai. And so here it is put onto a wall. The wall becomes very important in a moment. Right? So how is what I'm saying different from sort of Humeanism about laws? So one very standard gloss of Humeanism about laws centers around it enforcing a sort of metaphysical ban on necessary connections between distinct entities or existences, right? And so on this lens, what I'm calling dynamics first views are distinct from Humeanism about laws. For instance, on the dynamics first view, the laws on the dynamics first view of laws, the generalized Humean mosaic could include things like dispositions, right? Which you can see this work by Heather Demarest to see how that might work. She generalizes the Lewis best systems analysis to include dispositions. It's an interesting read. So there is, however, an alternate way of thinking about Humeanism, which what I'm saying is in line with. So the thought there is that one can parallel one's account of metaphysics with the actual methodology of science, and thereby achieve a relatively sparse metaphysics. So in this sort of way, I am following on with this Humean line of thought. Right? So dynamics first views of laws, geometry, space-time, whatever we're talking about, are in this sense unofficially Humean. Right? What they are is they're marked by this merely a codification of certain patterns in the dynamical behavior of matter. Right? This sort of style of doing metaphysics, which will become clear later on as I talk about it. I just wanted to put that out now, that this is not exactly a standard version of Humeanism that I'm talking about here. It could be. You could reinforce that necessary connections ban, but I'm not considering that as a necessary part of this view. Okay, so that was the primer on the metaphysics of laws debate. Let's now move on to an analogous debate about geometry. So the question here is, can the world's geometric structure help us explain the dynamical behavior of matter? You might have questions such as, why does every kind of force-free particle move in a straight line? Right? And why do all kinds of clocks, analog, digital, atomic, biological, whatever their working mechanism is, they all seem to exhibit the same sort of time dilation? And so we could appeal to individual laws in each individual case to find out why this is, but why do they all do this generally? Why is there some sort of common behavior across different physical systems? And a stock answer to this, if we're allowed to appeal to geometry, is the following. So for every kind of particle or clock, you can investigate their dynamics and codify these into laws. And we've done this. And it turns out that whenever you write these laws in a generally covariant way, at least, the laws all seem to make reference to a common geometric structure. And I'll show what that is in a few slides. But roughly you would say then that the existence of this common geometrical underpinning explains all the common dynamical behaviors of the particles and the clocks and all these things, right? But just as before, we can stop here and ask, do we like this geometry to dynamics explanatory strategy? And we can ask, what sort of metaphysical backstory do we need to support it? So the question in general, and I'm moving into a special relativistic context here just for simplicity. The question, I'll flesh it out a bit more, is what explains these composition-independent inertia and time dilation? Why do those effects appear across many, many systems with different compositions? So here's a few laws listed on the right, which arise when you sort of formulate these things carefully in a generally covariant way. And they involve these terms which I've listed on the left-hand side. And don't worry about the details if the math's unfamiliar to you. So we have a Lorentzian metric here. We have a covariant derivative and a scalar field and a tangent vector for a particle's trajectory. And those are all come together in these ways to be these sort of three laws. So the first law is the Klein-Gordon equation with some mass. The second law is Newton's second law in a special relativistic context. And the third law says that particles move forward in time. They move on time-like trajectories. So like I said, equation 2 says that force-free particles travel on straight lines. But the point is that when you write these things down carefully, some extra bits of structure show up. You have the particles and their trajectories, but you also have these metrical things and this covariant derivative and this Lorentzian metric. These show up here, and these are what sets the standard of straightness for the particle to follow. Particles don't just know which way straight is. At least it seems like there's some sort of geometrical structure to the world which they have to consult with to find out what straight is, right? So here, that's this eta AB and this nabla C object. And this happens in general. So in general, when you write down the laws of nature in a generally covariant way, they all seem to reference a common geometric structure. And in that case, it was eta AB and this connection, right? We can then ask, what's the metaphysical status of these geometric structures? They've shown up in our equations. We might not think the laws are anything metaphysically substantial, but these are things which appear in the laws, potentially on the same footing as the matter fields. So what are they? What should we think of them? So here you can adopt a geometry first view, and you say that these bits of geometric structure, well, they are metaphysically substantial things in the world. There's a space-time manifold, and it really has these geometric properties to it. There's sort of geometric fields which tell us what distances are and which directions are straight and all these things. So hence, with that geometric structure, the space-time manifold is also geometric in nature, and it has a locally Poincare invariant structure. Hence, the dynamical laws must be Poincare invariant. They follow along with the geometry. So hence we see time dilation in every kind of clock, and moreover we see straight line motion in all kinds of force-free particles. So the error of explanation here is from geometry to dynamics. The geometry sets up a certain structure for the space-time. This somehow influences what the dynamical laws are, and therefore indirectly influences the dynamical behavior of matter. That's sort of this story on this dynamics second view of geometry. We can, however, consider a more deflationary account of geometry, a la Brown or Huggett. These guys might say that the world's geometric structure are not anything metaphysically substantial, but they're merely codifications of certain patterns in the dynamical behavior of matter. And here the error of explanation has been reversed. These are dynamics first views, which point the error from dynamics to geometry. So we're explaining the geometric structure of the world in terms of dynamics. We don't think there's anything more to geometry than that. The primary benefit of these views is, like before, metaphysical sparsity. We don't have any spooky geometric objects floating around. The primary cost, though, is that we lose access to geometry-based, metaphysically supported explanations of dynamics. And again, metaphysically supported here means that there's actually some metaphysical force to the explanation, and it's not just a sort of unifying explanation. We can unify things and say, oh, there's this common structure they all sort of refer to, but not take it metaphysically seriously. And this sort of unifies things, but it doesn't explain why the particles know, or how the particles come to know which direction straight is, right? So we can go back then to this generalized Humean mosaic, and we can say, where are these geometric structures in the generalized Humean mosaic? You can identify them, more or less, with the wall which the mosaic is painted on. So the fact that the mosaic is on a wall is important, right? But does this sort of unofficially Humean view I'm putting forward implicitly assume that there's some geometric structure to the mosaic? Does it need these geometric underpinnings? So here we can go to Nick Huggett's work on regularity relationism, which offers a sort of mathematical picture of the fact that we don't need this geometrical underpinnings. And so here's just a rough gloss, a sort of pictorial view of what his view is saying. So consider the following sort of 3-step paint peeling process. What you do is you carefully peel all of the paint off of the Humean mosaic, and you imagine that this detached paint sheet is topologically connected. So it can bend and stretch at will, and there's no more notions of distance or of straight lines or anything like this. This can all be bent and stretched as we want, but there's still a topological connectedness to it. Right? So what we do is we find a good way of bending or stretching this detached paint sheet, and then what we do is place it back on the wall. And so the wall is where the geometric structure is, but how the matter relates to that geometric structure is actually a choice for us to make about how we bend and stretch the matter before we associate it with this geometric structure. And so roughly, a good way of bending and stretching this paint sheet will be one which fits well with the theories dynamics and kinematics. So we do some process of exploration, and it's like the Lewisian and best systems analysis in that we explore these and we find which one's best, and then that, like those are the laws, this is the geometric structure of the world, whichever is best suited to the dynamics and kinematics that we're dealing with. So, in particular, applying Huggett's view to this to a space-time theory will reveal of it the sort of following fact. I call it a geometric regularity fact. And this is my view of, I'm the one who's codifying Huggett's view into this sort of regularity fact. But I think he would go along with it. So we can conceptualize the dynamical behavior of matter in a geometry-independent way, namely as a detached paint sheet. And then from this geometry-neutral perspective, we can consider various ways of bending and stretching this detached paint sheet. One way of doing so in particular gives rise to nice geometric laws. And on a dynamics first view of geometry, this is all there is to the world's geometric structure. It is just a codification of a regularity fact, something like this one. So that's the metaphysics of laws debate and the dynamical geometrical spacetime debate. And hopefully you can see how they're related. I'm going to focus on those relationships now and build out the dynamics first versus dynamics second debates generally. So as I've mentioned, dynamics first and dynamics second views differ on the arrow of explanation. So on a dynamics second view, something, it's going to be laws, geometry, space-time, something helps us explain dynamics. This is some sort of unseen substructure to the world which helps us. On a dynamics first view, we're going to reverse that, and we're going to say that dynamics is actually what explains the substructure. But knowledge generation in science is a sort of dynamics first thing. We come to know the world's laws and its geometric structure and or its topological structure indirectly by studying and codifying the dynamical behavior of matter. And hence, we can rewrite this dynamics first, dynamics second distinction in terms of knowledge in this way. So dynamics second views have knowledge and explanation anti-parallel to each other. So we know about dynamics more directly, and then less directly we know about the substructure to the world. And then the substructure, though, is supposed to help us explain dynamics. Right? And on dynamics first view, we have just the opposite. Our knowledge and explanation go in the same direction. So we know more directly about dynamics, and we explain what we know less directly in terms of dynamics. So we can bring in a third factor here, though, which is metaphysics. And if we demand that our explanations are metaphysically supported, then explanation and metaphysics get tied together in some way. Right? So metaphysics and explanation must be together. And so now we have three arrows, and they could either be parallel or anti-parallel. Right? So here's roughly the story. Suppose that in studying the dynamical behavior of matter, this reveals some substructure to the world. It could be law-like or geometric or topological, really whatever. It reveals some substructure to the world. On dynamic second views, we take sort of a Platonic approach to this, and we say that this revealed substructure is actually metaphysically substantial. We've discovered something metaphysically substantial about the world through these investigations, and subsequently this will help us explain the dynamics. So we have the world of appearances, and then we discover some truer thing, and this actually helps inform and clarify what's going on with the dynamics. And it helps us explain why the dynamics is the way it is. Dynamics first views do the opposite, and they are, as I've mentioned, sort of unofficially Humean. They may be thoroughgoing Humeans if they want to be, but they're sort of unofficially Humean in the way I talked about. So this revealed substructure is taken to be metaphysically deflated. So it's just a codification of the dynamical behavior of matter. We don't think the laws are anything substantial. Maybe we don't think the geometry is anything substantial. Or maybe we don't think that the spacetime manifold is anything sort of metaphysically substantial, past being a codification of patterns. Perhaps a really salient one. I mean, some of these patterns really pop at you, and it's very, very hard to ignore them, and they seem like they're real, or that there's something to them, but they are just patterns, and we ought to think of them as such. Right? So that's a dynamics first view. And this is, in some sense, the sparsest metaphysics that's consistent with scientific practice, because it has this aligning of knowledge and metaphysics. Right? It has its benefits there. So these are the benefits of dynamics first views. So they have a sort of favorable three-way alignment between explanation and metaphysics and knowledge. And this three-way alignment yields, in some sense, the sparsest metaphysics consistent with scientific practice. Right? And so why? Because the metaphysics is based on scientific practice. Right? And so why put forward a dynamics first view of the spacetime manifold? In order to bring the metaphysical sparsity, which is characteristic of these dynamics first views, to the philosophy of space and time. Right? So it's extending this debate about laws and geometry, extending it into topology. This is what we're up to. So now we're in a position to develop and to state this dynamics first view of the spacetime manifold. So the claim will be that the world's topological structure, like the spacetime manifold, is merely a codification of patterns in the dynamical behavior of matter. So let's go back to this generalized Humean mosaic. Where is the topological structure in this generalized Humean mosaic? Does a sort of unofficially Humean view implicitly assume it? Does the mosaic need its topological underpinnings, or can we somehow get rid of them? Let's go back to Huggett's paint peeling process. Again, we peel the paint off the wall, we imagine it's stretchable and bendable, and then we select a good way of bending it and stretching it and then put it back on the wall. Right? And so Norton has a paper from 2008 where he notes that this detached paint sheet is still topologically connected. So we still have a sort of topological structure. Once the paint sheet is removed, it's still topological, right? And so if we're going to get rid of the topological structure, we need to somehow divorce it from the dynamical behavior of matter, right? We got rid of the geometry already, now let's get rid of the topology. So we need an upgrade. So there's a three-step process I put forward for doing this. And unfortunately, the technical details of this, I'm not going to be able to cover them in this presentation, but you can find them all in the paper. And I may publish or put out a technical explainer video after this one. But for now, let's just get the concepts clear, and I'll work through some examples which will demonstrate some of the bare bones of those concepts. Right? But anyway, so the first step is internalize. So what I've called this is the internalize, search, externalize, or the ISE methodology. So the first step is internalize. We move to a space-time independent view of our theory through a process of internalization. And this is where we reduce our space-time theory down to its sort of vectorial, or more generally, if we have nonlinear dynamics, we're going to need something algebraic to a core of algebra or geometry, or algebra or vectors. Right? And this is analogous to peeling the paint off of the wall. So now we have some sort of algebraic paint without any topological structure to it. And from the paint metaphor obviously breaks down at this point. So from this space-time neutral perspective, what we can do is search for various pre-space-time translation operations. And this is again a term of jargon which is explained in detail in the paper, but we're just going to get a sense of how it works now. So this is analogous, the second step, to searching for good ways of bending or stretching the detached paint sheet. So we take the paint out of its topological underpinnings, and then we consider various ways of finding pre-spacetime translation operations. And once we found good ones, what do we do with them? So after selecting some good pre-spacetime translation operations, we build a new spacetime setting for the theory via a process of externalization. And again, the technical details are in the paper, but we'll get a sense of how that happens now. Roughly, what happens is externalization takes some hand-picked pre-spacetime translation operations. There's a wide variety of them for us to choose from. We just pick some, and then it lets them be honest-to-goodness spacetime translations, right? And there's a definition for pre-spacetime translation operations which makes this make sense. So these are the sorts of objects which we can generate a spacetime from, and there's a lot of them. Right? And this is analogous to putting the detached paint sheet back on the wall. And so what it means for a pre-spacetime translation operation to be good is that it yields a spacetime setting which fits well with the theory's dynamics and kinematics, right? And our understanding of the theory and its relationship to other theories. So that's the three-step process. And then we're going to prove from that what I'm going to call a topological regularity fact, which is very much like the geometric regularity fact I talked about earlier. So given some amount of space-time kinematic compatibility, and again, the technical details are in the paper, but I'll give you a sense of what it means in the examples. So given some space-time kinematic compatibility, what we do is we apply this ISE methodology. So we take the paint off, and then we change it somehow, and then we put it back on. But it's not paint because it's just algebra. So there's some sort of algebraic metaphysics going on, which I'm not going to comment much on, but that we have a mathematical process for generating new spacetimes. Okay. So what this means is that we can conceptualize of the dynamical behavior of matter in a spacetime independent way, namely via internalization. And from this spacetime neutral perspective, we can consider various ways of picking out which pre-spacetime translation operations to externalize. One way of doing so in particular gives rise to nice laws set on a smooth topological manifold. So that's the topological regularity fact, and the dynamics first view of the spacetime manifold, which I'm putting forward, says that the world's topological structure, i.e. the spacetime manifold, is merely a codification of this regularity fact. So next, I'll move on to demonstrate this view with some example applications.